Imagine that you are in a corner of a room, and on the other side, in the opposite corner, there is a lamp. Now, this lamp is plugged into the outlet, and so it's shining bright, but you don't want it to be shining bright. You'd like to turn it off, or to be more precise, you'd like to control when it's on or off from the other side of the room. So, how could you do it? Well, a simple idea would be to connect another cable to the first cable using a MOSFET or something like that. That way, if you let electricity pass through your cable, then you can turn on the lamp, or you can turn it off. So that works, but what else could we do? We could do it using waves, electromagnetic for example, by having a controller emit some kind of infrared radiation and having a detector pick it up on the cable. But there's more than one way to skin a bat here. We could also use sound, which is another type of wave, using a clapper, so a sensor that turns the flow of electricity on or off by detecting a clap. But why stop there? You could also use light, or collision, or temperature, or water, or crabs, or anything actually. And hold on, there is a pretty interesting question to be asked here. What are you actually moving? To be precise, you are on this side of the room and the lamp is on the other side, which means that what we want to do is move something from this position to this position. But what are we moving? You could say that electricity would be what we're moving, and that would track with the cable and the light, but it wouldn't really work for other things. So another suggestion could be energy, which certainly would track. I mean, all of those things are energy, but energy is extremely general, and in this case what we're transferring is not proportional to energy. What's more, depending on what transistors you have, flow of electricity could mean lamp on, or lack of electricity could mean lamp on, which is inverse to energy. So what are we actually moving? Well, what we're moving is information. And that's what this video will be about. It will be a first of a series in which I explain exactly how computers work, and today it will be an introduction to information. But wait a second, what even is information? That is a much more difficult question than it seems, so I'll mostly pick it up in the next episode of this series, but for now, all that's important is the fact that information is disconnected from any specific thing. It could be electricity, it could be water, it could be crabs, it could be anything. So from now on, we'll refer to it just by logic. So we'll have logic cables which could be either on or off, or yes or no, or 1 or 0, or A or B, or bright and dim. It's all irrelevant because we're not dealing with anything physical, we're dealing with hypothetical. The implementation will come later on, but for now we'll just talk about pure logic. So how will our logic function? For that we'll need some logic gates, 3 of them to be exact. The AND, the OR and the NOT. Now this is not an AND gate, only a NOT gate, or if you would prefer, not an OR gate or an AND gate, only a NOT gate and not a thing else. Hope that's clear to everyone. Now how do these gates function? Well, that's simple. An OR gate lights up if the first or the second input is lit. The AND gate lights up if the first and the second input is lit. The NOT gate lights up if the input is not lit. I'm just going to zoom out now and just go over them again just to make sure that it all makes sense. Okay, now how would we use these logic gates? Well, those logic gates are useful for automation. So for example, imagine that you have an apple and you'd like to figure out if you can eat that apple or not. In that case, a solid description of an apple that you could eat would be an apple which is not moldy and not green. And this sentence can be actually constructed using logic gates. So basically, if you create a system in which one of the inputs would tell you if an apple is moldy and the other one would tell you if it's green, then right here you add a NOT gate, and an AND gate, and there, you've created a system of logic gates which will tell you if you can eat that apple. Now this may not seem all that impressive, but even in that toy example it could be useful. If you get a machine that scans apples for being moldy, a machine that scans them for being green, you plug the input into the system, and there, you get your answer. Now obviously this was a toy example, but that is the half of how to create anything with logic. You just want to describe what you want with logic gates. What's the other half? Well, to get there, we need to first escape Blender into a different domain. Finally, we got there. It's oxygen not included. Hello everyone, welcome into yet another gaming video, and today we'll be playing one of my favorite games, Oxygen Not Included. We start by gathering some materials, building an outhouse, building a science thingy, exploiting Mother Nature for our gain, becoming all barren, setting up dictatorship, spreading propaganda, setting up a futuristic utopia, and killing off the lower classes. Okay, now that we've got this out of the way, we can begin the age of automation and machines, and we'll do it by using logic and logic gates. Okay, so just to get used to our new components, first we have the logic cable. The idea is really simple. We just connect the logic source to a logic destination. In this case, a logic source would be something like a switch, and a logic destination would be like a light. So we can turn our switch on, the light turns on. We can turn the switch off, the light turns off. Simple as it could be. Next, there are logic gates. We've already been over them and the rules don't change. NOT gate, OR gate, AND gate. Once again, simple as it could be. They all work the same way. Now there is one more thing before we can move on to building computers, and that's the thing that this chapter is actually about, and that's abstraction. And the best way to demonstrate that would be to tell you about the fourth gate, the XOR. So, what is XOR? Well, XOR is a gate that lights up if the first or the second output are both lit up, and not both. Now, this is obviously an extremely useful logic gate, so you might be wondering why I haven't mentioned it before, and the reason is that I did kind of mention it before. That's because XOR is not a basic logic gate, and can be made using other logic gates. Think about it this way. We've described the output of XOR as, well, XOR is a gate that lights up if the first or the second output are both lit up, and not both. First or second and not both. Both in this case just means first and second, which means that we can once again turn the sentence into a logic tree, and there we go, an XOR. You can see that it works just fine. I'll go over this again so that you can focus on any of these logic gates and see that it's actually working. Okay, there we go, that's an XOR gate, but where's the abstraction? Well, abstraction comes in the fact that we can package this entire deal of a logic gate into a new logic gate. And from now on, if we need to represent something that takes first or second but not both inputs, then we can just use a singular logic gate. We don't need this whole massive tree, we can just use this. But there's more than one culprit here. In Oxygen Not Included, we also have a memory toggle, which stores an input given to it until it's reset. This will be rather important in the next video about information, memory, and the way we use it, but in this video I'd like to focus on the fact that this is not, in fact, a basic logic gate. That's because it can be constructed using an OR gate, and an AND gate, and a NOT gate. How? Well, if you think about it, here's just a basic logic cable. Except if we want it to be memory, it should be on if it is on, or if it was on. Meaning that a simple OR gate like this would suffice. But there's one problem, our memory toggle has more than one input. It has input for memory and input for resetting it. So we would also want to check if it was on and it wasn't reset. Simple. So right here you can see once again the non-abstracted memory and abstracted memory. But let's keep going. Okay, before I explain this other, a brief lesson on binary. Once again, I'll do the actual explanation in the next video, but for now, let's just get the simplest one. In base 10, when you note down a number, then you take each digit of it and you multiply it by its respective power of 10. In binary, you do the exact same thing, except the maximum number is 1 and the power is 2. That way, this is how you count up in binary. And that's how computers store numbers. Now, this is not how they do it at all. It really depends a lot more on interpretation than the stored information. Okay, listen, you'll get your own video, alright? Can I please finish my present video before we finish your future video? I'm just saying, okay? I don't want you to oversimplify too much. Listen, we're talking about the MAKiT video. Obviously, it's gonna be oversimplified. Now, would you mind not breaking the time continuum and let me finish my video? Fine. Thank you. Okay, where were we? Oh yeah, right, binary. Meaning that if we have two-digit binary number, this would be a 0, a 1, a 2, and a 3. Cool, now with that in mind, we can try to implement a simple circuit to add two numbers together. Or to be more precise, two single-digit binary numbers into a two-digit binary number. How would we do it? Well, let's take a look at a bunch of inputs and their corresponding outputs. Okay, now you can see that the second output lights up if both inputs are on. So if the first and the second inputs are on. That's simple. But what about the first? Well, the first lights up if the first or the second light up, but not both. And wouldn't you know it, we don't need to express all of these complex gates. Instead, we can just say XOR. It's simple. Now if we take a look at the full circuit, it works. Lovely. Which means that now we can add together two numbers. But there is a bit of a pickle. You see, we're not really utilizing the full might of our 2 bits. That's because the highest number they could express is 3, but we only get 2. So now we could add one more bit to get the full adder, and honestly it's just one more bit, so it wouldn't be all that difficult. We just need to add like a... Oh, alright, that's a... that's a fair bit larger than it has to be, but... Okay, whatever, let's break it down. First, let's color in the logic gates to make them clearer. There. Now we can realize one thing, and that's the fact that in an adder, we don't really care about which bit specifically is on. We want it to be symmetric. So if we look at the table of inputs to outputs, you can see that we don't really care about any specific bit. Instead, we can simplify it to no bits, 1 bit, 2 bits, or all bits. And now with that in mind, we can get back to our circuit and break it down into these 3 sections. What do they do? Well, the first one is just 2 OR gates, so it tells you if the first, or the second, or the third inputs are on. Or in other words, it tells you if at least one input is on. Then the second group is just 2 AND gates, which in turn tell you if the first and the second and the third input is on. Or in other words, if all 3 inputs are on. Now the third one tells us if the first and second, or second and third, or third and first are on, or in other words, if at least 2 of them are on. Now we can abstract these away, and instead of focusing on the logic gates themselves, we can focus on the clusters and what they do. For example, if we add a NOT and an AND here, we can check if at least 2 inputs are on, and if not, 3 inputs are on. Or in other words, if exactly 2 inputs are on. Now we can take it, we can check if at least 1 is on, and if not exactly 2 are on, meaning if 1 or 3 are on. I know it's a lot of words, but I really would encourage you to go through it logically, not the logic gates themselves, but the sentences, because the sentences are equivalent to the logic gates. And there, now you can see that from this confusing mess of logic gates, we've actually gotten quite a few reasonable outputs. Now the task of making a full bit adder is much easier, because going back to our table of inputs and outputs, we can see that we just need to light up this bit if it's 1 or 3, and this bit if it's 2 and 3. And there, it's finished. A full adder. Now why is the full adder better? Because of this. Yeah, if you thought that previous thing was big, then this is an 8-bit adder, an adder which you can use to sum together 2 8-bit numbers, so numbers between 0 and 255. How does it work? Well, it's actually really simple. First, let's get the annoying details. These bundles right here are just the multiple logic cables tied together, 4 of them to be exact, and these little things are used for reading and writing respectively. It's just a minor convenience thing in order to move a lot of data at the same time. Now with that in mind, we can analyze how this works, and you can see there is a certain degree of recursiveness to it. Like, all of these look pretty gosh dang similar, don't they? What's the deal there? Well, they look similar because they're actually the same thing. These are all just full adders plugged into each other. So each adder has 3 inputs, 2 outputs, and they are wired like this. That's because for each 2 digits we add them together, we take the result. If the result is 2 digits large, we pass the second digit into the next adder. It's the same way as you do addition in base 10, so if you think about it for a second, you realize how simple it is. Now with that in mind, our adder is kind of trivial actually. If you take a look at it again, you can realize there's just 8 adders. And that's it. It's just 8 of them. And this is actually the best example of how abstraction works. You see, this circuit looks really massive, large and scary, but if you zoom in, the individual logic gates are pretty simple. The more complex logic gates are pretty simple if you abstract. The logic clusters are pretty simple if you abstract. The individual components are pretty simple if you abstract, and that's actually it. We've reached the 8-bit adder. And that's how computers work, that's how they are made. The 3 main concepts underlying them: the logic medium, basic logic operations, and abstraction. In future videos I'll go more in depth, explaining things like information, memory, networking, programming, and heck, maybe even I'll build a sick-ass robot if we get enough patrons. But for now, there is one more thing I'd like to mention, and that's the fact that all 3 of these things are disconnected from any kind of implementation. Which means that if I show you this kind of 4-bit adder, this is just theoretical logic, and we can implement it in theory, in Blender, in Oxygen not included, or even in real life. And so now, I'm sorry, what's that? In 3 days, so I guess we'll implement this another time because, you know, I just had to finish this video in 3 days. If I sound a bit rough, I'm sorry, but right now I'm at the end of my 22-hour work day, and if you'd like to see me actually do this logic in real life, actually implement it in real life for future videos, then you can support me on Patreon. And speaking of that, thank you to all my patrons. Special thanks to Useless Quasar, Acronymus, and Legbe for being highest tier patrons. Thank you all so much, and thank you to all my other patrons for allowing me to spend this much time on this quick video. I am not doing well. I also stream every single day. Fun fact, actually a portion of this video I have made on stream. 10 digits, where you get 10 digits from that? Not 8. It's 450 MAKiT. Ah, that checks out. 9 digits. Now it's my machine does better maths than me. The other I have made in Oxygen not included does better maths than me. It's a series of live streams called Charity Checkups, which we stream for charity. Right now we're collecting money for charity Prevent Cancer Foundation. It's a lot of fun. I also have a Discord server, we can join in, chat. It's once again fun. And I think that's it. I'm gonna go get back to work on the other videos, and for now that'll be it. Thank you so much for watching, have a great day. Bye.